This is a presentation that was originally done in Hong Kong in October 2000. First we'll talk about materials on photovoltaics. And of course there's single crystal, polycrystal, thin film, and various thin films, amorphous, copper and diselenide, and cadmium telluride. Single crystal's advantage, it's a proven technology, it lasts a long time with 25-year warranties, and can be used from waste in the computer industry. But actually these days the photovoltaic industry uses more silicon than the computer industry. The disadvantages is that the efficiencies have peaked. Single crystal takes a lot of energy to make it into modules and systems. The round shape can cause loss in material usage. It's expensive when competing with high-grade silicon. It's also fragile. Polycrystal has similar advantages, but it takes less energy to manufacture, uses a lower grade silicon, can again use from computer industries stock, and square as opposed to round. The disadvantages is this is less efficient because of grain boundaries. The thickness has been reduced to a point where it will cause breakage in the future if not really addressed properly. It has a low efficiency, and again, it's fragile. So then there's thin film amorphous. A lot less energy to produce, smaller amounts of material is used. It's got good area utilization and can be deposited on various kinds of material like glass. Encapsulations has a long life because the weather can't get in. If you have a glass sandwich, it just is around the edges where the weather can penetrate. Disadvantages, it's low efficiency. There's needs bypass diodes, so each cell in the larger configuration like this one in the background uses bypass diodes. Needs to be deposited on materials that won't break, and it's expensive to start up an assembly line. Copper diselenide has high theoretical efficiencies. It's not harmful to the environment, easy to produce once a factory is operational, and it can be put on flexible substrates. Disadvantages is that there's not a lot of it available yet. Temperature coefficients are 4%. Doesn't work as well as amorphous silicon, but it works better than crystalline silicon. Cadmium telluride. It's high efficiencies again, theoretically, easy to deposit, and it has low cost opportunities. And the disadvantage, cadmium is carcinogenic, environmentally dangerous in manufacturing and disposal. There are some cradle-to-cradle strategies to address that. I-V curve is what electrical engineers like to look at for photovoltaics, and this graph tells some great information. It's the max power current and the short circuit current, max power voltage, and the open circuit voltage. And this is the max power point where ideally system operates right about that point on the knee of the curve. That changes with various different temperatures, and this would be for a crystal silicon. The knee is in a different place depending on different operating temperatures, so you have to adjust accordingly with balance of systems equipment. The end.